All right, we'll get started here in just a second, getting everything up. All right, so welcome. This will be our first lesson in our Chemistry of Life unit that has to do with the biochemical nature of life. And I first just wanted to make sure to do a good, really review of some core concepts from chemistry that are going to be important for us in biology, both as a nice refresher to focus what you might recall if you've taken chemistry, and for those who haven't, just to give you the knowledge that you will need specifically for this unit as far as things that will have come from the chemistry course that we'll need to utilize. So in either case, don't worry, we're going to go over here today pretty thoroughly those things we need to know or we need to remember. And then always, I would suggest signing up for the AP Bio A Plus on Tuesdays each week, if there, especially here at the beginning, if there are things with chemistry that after today you don't feel so comfortable with, because I really want to make sure that we all start out feeling good about this part. So, chemistry is foundational to biology. All living things are basically giant, complex chemical machines. And so the properties of all living things are emergent from the chemical properties of their substituent molecules. So, in that end, we're not going to have to necessarily remember all of the nuances with things like orbital notation or um, enthalpies of reaction like you might have done in chemistry or naming compounds, but there are a few things that I want to make sure to stress today and go over. So one thing that we are just going to need to remember is just the basic structure of atoms. So atoms are made up of three parts: protons, which are in the center of the atom called the nucleus, and they're positively charged; neutrons, which are also in the center or the nucleus of an atom, and they're neutrally charged; and electrons, which are on the outside of the atom and they're negatively charged, right? And in general, in a neutral atom, so an atom that isn't an ion, meaning it's not in total negative or positive, the number of protons and the number of electrons are the same number for neutral atoms. Now notice on these pictures here, I'm using Bohr models because that will be sufficient to explain everything that we need to know about atoms for biology. So even though you might have learned about the wave model in chemistry, we're not using those because they are unnecessarily complex for our purposes. So in chemistry, you probably talked a lot about the periodic table with all 120 different elements, and I have a picture up here of the periodic table. And so just remember that each element is a different kind of atom. They have a different number of protons and different number of electrons. So, the numbers that we see up here called the atomic number, they tell us the number of protons that are in the nucleus and also the number of electrons around the atom for neutral atoms of each element. But the good news is, in biology, we don't need to worry about all of these different atoms, all of these different elements. In fact, we just really need to focus on 8 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, there's 10 kind of here. But in the next slide, you'll see that there are 8 specific elements that are going to be the most important for us to remember about. So don't feel worried or overwhelmed that we have to memorize the periodic table or know a bunch about all these different types of elements. In truth, we're mainly going to be focusing on 8. And here we are. So life requires about 25 different chemical elements. And of those, 4 of them, carbon, oxygen, hydrogen, and nitrogen, make up about 96% of all living matter. So those are the most important for us to keep in mind and to know about: carbon, oxygen, hydrogen, and nitrogen. Of the remaining 4%, phosphorus, sulfur, calcium, and potassium makes up most of that 4%. So you can think almost 99% or more than 99% of all living matter is made up of these 8 elements you see on the screen. The other elements of those 25 that aren't composed of these 8, we call trace elements because life just requires a small, minute amount of those. But it's these 8 that you will see in diagrams all the time and that you'll see referred into in your text and activities that we do. So these are the key ones kind of to focus on. One of the things that atoms can do is they can bond together. They can bond or stick together. And bonds are extremely important in biology because that's how tissues and organs are constructed from smaller molecules. And bonding has everything to do with electrons. So here's an atom, and you can see the electrons distributed around the different energy levels, orbits, or shells. And bonds specifically have to do with these electrons represented by red dots in the outermost shell. So here's the nucleus, this blue chunk in the middle, the outermost electrons in what we call the valence shell. And so these are called valence electrons. And the number of valence electrons that an atom has or an element has influences how that element behaves, what it reacts with, what it can form a bond with, what it can't form a bond with. So that's extremely important. So if you notice here on the left, I have an atom that has 1, 2, 3, 4, 5, 6 valence electrons. And so it's going to behave very differently than this atom on the right that has 1, 2 valence electrons. So valence electrons determine the behavior, the chemical reactivity of different atoms, and influences what it can and can't bond with under what conditions. So here is a slice of the periodic table. Notice that the central section of the periodic table was removed. It goes from lithium, beryllium, then to boron. So if we go back to our periodic table here, it's cutting out this middle section. This middle section we won't really worry about. You most likely didn't do a ton with it in chemistry anyway. So when we look at this periodic table here that cuts out the middle section, we can see a pattern becoming established as far as the number of orbits or shells and number of valence electrons on the periodic table. So first, notice how as we go down rows in our periodic table, we add shells. So this first row has 1, and the second row has 1, 2 shells or orbits, and the third row has 1, 2, 3 shells or orbits. So elements in the same row have the same number of shells. All of these have 1, all of these have 2, all of these have 3, kind of as you can see here. If we go from the left side of the periodic table to the right, each element has an additional valence electron. So look at in this first column, all of them have 1, 1, 1. In the second column, 2, 2, 2, 3, 3, 3, all the way up to 8. So 8, except for helium, right? Helium only has 2. And we got 7 and 6. And then from the left, all of these in the first row have 1 valence electron, then 2. So it follows a sequential pattern. Atoms tend to want to complete a partially filled valence shell or empty a partially filled valence shell to become chemically stable. What do I mean by that? Except for hydrogen and helium, all the other elements that we're going to talk about are the most energetically stable when they have 8 electrons in their outermost orbit. We say they have a full valence shell. Helium and hydrogen are most stable when they have 2 electrons in their outermost shell. So excepting for helium and hydrogen, all the other elements want 8. So elements that have 5, 6, or 7 valence electrons tend to gain them through chemical reactions to get to 8 and be energetically stable. Elements that have 1, 2, or 3 valence electrons tend to lose them to have a full valence shell and be chemically stable. And this tendency is what makes chemical reactions possible. That's why bonds are created, so that elements can gain their preferred number of valence electrons and be energetically stable. So in biology, the strength of bonds is very important because it dictates how different molecules react with one another. So some examples of weak bonds are up on the top, and specific, as we go through our unit, we'll learn about the first two specifically. And we'll talk about today strong bonds, these last two, covalent and ionic bonds. So covalent bonds are really strong because the atoms that participate in covalent bonds share electrons between them so that they can become energetically stable. Both atoms are holding on to electrons together. So think about it, if you have like two little kids fighting over a toy and they're both grabbing it and pulling on it. They both want to pull it towards themselves. And in so doing, they're attached to one another. They are stuck together. It's very much the same for covalent bonds. And when we covalent bonds form, the atoms join together to form molecules. So for example, here's hydrogen gas. Remember, hydrogen and helium are both most energetically stable when they have two valence electrons. And so by each of these hydrogen atoms, which normally have one valence electron, sharing with the other one, they can form a covalent bond in which they're stable, having two. Here we have a water molecule of one oxygen and two hydrogen atoms. And normally oxygen has 6 valence electrons and each hydrogen has 1. And when they are able to share with one another like this, we can see that oxygen is able to get 2, 4, 6, 8 valence electrons, and also each hydrogen is able to get 2 valence electrons, and so they're all energetically stable like this, and so this strong covalent bond here and here forms. Now, there's nothing stopping an atom from forming more than one covalent bond um, if that will allow them to be more stable. So two atoms can share more than one pair of electrons to form double bonds if two pairs are shared, or triple bonds where three pairs are shared. And the more pairs of electrons that are being shared, the stronger the bond is, the more energy needs to be put in to break it. Okay, another really important um, concept from chemistry that has a lot to do with bonding is electronegativity. So electronegativity is the ability of an atom to attract electrons when bonded. So when bonded like this, um, electronegativity is a measure of how strongly each of these atoms pull on the electrons. So you can, if we think about that analogy with the two kids fighting over the toy, electronegativity is like how strong each of those kids are. How much can each child pull on the toy towards themselves? And luckily, if you look at this periodic table, there's a pattern in electronegativity on the periodic table. So when we look at the periodic table, electronegativity increases as we go from the left side of our periodic table towards the right side. And it also increases going from the bottom of the periodic table to the top. So things that are over in the top right are the most electronegative, meaning they are able to pull on electrons that are shared in bonds more strongly, and those elements that have very low electronegativity are very weak at pulling on the electrons are on the lower left side right here. And so you can see on the right kind of some numerical, so quantitative um, data as far as how electronegative different elements are. So fluorine is the most electronegative element, and francium down here is the least electronegative element. Remembering that general pattern of uh, electronegativity increasing from left to right and from bottom to top will help us remember the key things as far as how electronegative different elements are. So when electrons are shared between two atoms, a covalent bond is formed. We kind of already talked about that. If the atoms are identical, like, for example, two chlorines sharing electrons, the electrons are shared equally, and we tend to call those substances nonpolar. So here's an example of chlorine. Chlorine gas molecule, two chlorine atoms covalently bonded together. And since those two elements, chlorine in itself, are equally able to attract electrons, they're equal in electronegativity, one of them isn't pulling on the electrons more strongly than the other, we call this molecule nonpolar. And you can see an electron distribution diagram here, which is a kind of color-coded way to show that it's nonpolar. Okay. On the other hand, if the electrons are shared between two different atoms, like hydrogen and bromine, the sharing might be unequal. The bonding electrons spend more time near the more electronegative element because just like the kid that's stronger pulling on the toy, it can pull the toy closer to itself. The more electronegative element can pull the electrons closer to itself. And so we get something that's called a polar covalent bond. So here's bromine, here's hydrogen. If we go back to that periodic table, bromine is right here, bromine, sorry, is right here. Hydrogen is right here. If we notice, they have a difference in electronegativity. Bromine, sorry, is more electronegative. It's 2.5 to 2.9, whereas hydrogen is closer to 2. Okay, so that means that bromine is able to pull on those electrons more strongly than hydrogen. And so the electrons tend to gravitate towards the bromine side of this bond. They're not shared right down the middle equally. And since more negative electrons are closer to the bromine than the hydrogen, the side of this molecule, this two-atom molecule, closer to the bromine is slightly more negative because there's more negative electrons closer to that side. And the side of the molecule, this two-atom molecule where the hydrogen is slightly positive because there's electrons farther away from that side. So we call this a polar molecule because we can define a slightly positive side and a slightly negative side, just kind of like there is two poles on a magnet, a north and a south. We can have a plus and a minus pole or side to this molecule, so we call it polar. So, the absolute value of the difference in electronegativities of two bonded atoms provide a measure of polarity of a bond. So, the greater the difference, the more polar the bond. Polarity isn't a simple yes or no. This is polar, this is nonpolar. It is a spectrum. Okay? So, it is a spectrum. If the difference between the two atoms is between 0 and 0.4 as far as electronegativity, we say that that bond between the two is nonpolar covalent. So if we go back to our table here and we pick two atoms and the difference between their electronegativities, say, okay, here's carbon and hydrogen is probably like 2.4 and carbon is like 2.5. Well, that difference is only 0.1. And so, according to like our chart here, that would be a nonpolar covalent bond. Now, if that difference is greater, like 0.41 to 1.69, that's a polar covalent bond. Anything greater than that will usually only be found in ionic bonds. So really, we're going to use this idea of difference in electronegativities to understand that it's not a yes or no. It's kind of a spectrum of more polar or less polar. It's used for a comparison. One of the things that we should be able to see now is that not just bonds, but whole molecules can be more polar or more nonpolar. So, polar covalent bonds, like we said, are formed by pairs of electrons that are shared unequally between atoms. So, in a water molecule, there are two hydrogen-oxygen bonds. Okay, and if we look back at our table of electronegativities, oxygen has a between 3 and 4 electronegativity. Actually, it's 3.5. And hydrogen has between a 2 and 2.4. It's more of a 2. So the difference between hydrogen and oxygen is about 1.5 on the electronegativity spectrum. And so according to that table we looked at, 1.5 is in the polar covalent range. So both of these bonds are polar, meaning that oxygen is pulling on those electrons more strongly than hydrogen. And so the electrons will be more closely, or will be pulled closer to the oxygen than the hydrogen. They're more strongly attracted towards the oxygen and less towards the hydrogen. Okay? Because of this, if we look at the molecule as a whole, the let me get my pencil out here. Okay, the area that is closer to the oxygen in this water molecule will be slightly negative, because there's more electrons surrounding this oxygen, and the area by each hydrogen will be slightly positive because the electrons, like these arrows are showing you, have moved away from the hydrogen. Okay, so we have these two nonpolar bonds, or polar bonds, I'm sorry. Because of that, notice how we can create this line. And this part up here, this side of the molecule is more negative than this side of the molecule down here. Because we're able to make this line, we can delineate a negative part of the molecule and a positive part. We call this a polar molecule. Here's the negative pole, and here's the positive pole, just kind of like a magnet or a battery. Because water is a polar molecule, and there's many other examples of a polar molecule, it will lead water to have many interesting properties that will be important for it as far as why it is necessary by all life that we know of. And talking more about those properties is going to be the center of our discussion next time. So, this time we talked about some key items from chemistry that led us to our most important concept of electronegativity and polarity. And those two things, more that electronegativity gives rise to polarity. Polarity is the central issue or the central understanding for today, and that we'll need to continue to improve upon or understand as we go through the next couple days worth of lessons. So, with that, that is it for today, and we'll talk next time.